today. As the title suggests, we're talking about particle-laden flows today. So these are things like slurries or dissolving systems or residence time distributions of diluting solids or whatnot. So looking at fluid mechanics, particle mechanics, different types of particle representations, as it were. Now we can use these types of mechanisms to model industrial transport processes. Just kind of cue everybody in. So we're talking about things like this. We're talking about, dissolving and agitation processes. Here we have, for example, a CFD DEM simulation of a non-uniform particle size batch that's being agitated by an impeller. We're dynamically adjusting the impeller speed in order to achieve a certain sort of suspension characteristic. I showed this before, but I'll be speaking more about this today. So again, we're seeing what fraction of the particles are being suspended as a function of the impeller speed. Again, this is combined CFD, this is combined DEM. Particles are hitting off each other, and the net effect of the fluid flow and the transport is a convolution of that two combined physics. The way the particles are informing the viscosity and doing work on the fluid, and the way the fluid is informing the transport via suspension, agitation, drag, etc. Here's an example of more of a finer simulation, what I'll introduce as resolved particles, where these particles are large compared to the eddy structure. They're actually resolved in the trailing vortices behind them. We're looking at how they fall, settle, tumble, etc. This might be for more of a tablet-like dissolution process or whatnot. But foundationally, it's the same kind of idea of this particle-based simulation, but it's a much different resolution and scope. We're focusing here on the fluid flow around the particle explicitly, not just using some unresolved particle, as I'll speak to momentarily. Here's more of an open system of just some sort of a particle accumulation process. I just have this range of particles coming in between 1 and 2 millimeters. This is CFD DEM again. So we're getting some packed bed down below, and the particles are sliding over it and filling each of these baffled regions behind it along the pipe. So again, a combined simulation. We look at buildup, accretion. We can look at resonance time distribution, how different particle size is realized, different RTDs and mean ages and whatnot. There's all sorts of particle-laden systems, combined particle dynamics, fluid dynamics. That's kind of the topic today. Again, as always, start with these slides. We're focusing entirely on GPU-based algorithms. Okay, this is all we run for, guys. And I'll die on this hill. If you're not running your simulations, your physics-based models entirely on GPUs, guys, I don't mean to be harsh, but you're doing it wrong. In 2024, there's no longer an excuse. And again, if you're running code and it's parity on GPUs or CPUs, you're doing it wrong. Okay. A GPU-based compute architecture is a step change in compute capacity. It is a step change in memory bandwidth. There should be a day in your life where you go from using CPUs to physics to doing GPUs. You should remember that day every day because it changes how you simulate. If you have not realized that step change in performance and speed, call. We can talk after the fact. But we're all about GPU-based physics-based modeling approaches here. Why? GPUs present tremendous compute density. GPUs present tremendous memory bandwidth, as it were. And GPUs are the reason why we're seeing all these advanced modeling functionalities, being able to model, CFD DEM simulations with tens or hundreds of millions of DEM particles on pretty modest desktop resources, or GPUs-based computing resources are why we can model, hours of transport. As I'll show today as we run these simulations, hours of physical processes. And again, this doesn't motivate us to do the same stuff faster. It changes how we do simulations. I show this slide every time. This is the spectrum of engineers think. We have correlations that are quick and dirty. They mask a lot of the physics, as it were, but they're very efficient to use. We can then go into continuum-based approaches like Navier-Stokes, Fourier's law, heat transfer, etc. They're great. This is where a lot of engineers operate when they're doing physics-based modeling. If we're doing a bit more foundational approaches, we can do model transport carriers. These would be the explicit particles or bubbles, or in the nanoscale system, the molecules, as it were. And then below all this, we have kind of axiomatic transport relationships like Schrodinger's equation. Foundation, the point of all this is not to run correlations faster. We're not trying to run the correlation a billion times faster. The point of all this is to drive our physics down to, or its more foundational transport representations that allow us to run with fewer assumptions and handle a broader case of problem sets. So the purpose of all of this is to punch down towards more foundational transport representations that eliminate the need for generalized correlations, that eliminate need for assumptions about material properties, allow us to model physics at the level of individual transport carriers, be it bubbles in a bioreactor, be it sand in a tank, be it particles solving, etc. So our discussion today is particles, solid systems, as I mentioned. And let me kind of give a roadmap over where we're going. I'm first going to introduce kind of different classes of particles, tracers, inertial, and DEM in particular. Tracers, as introduced, are non-inertial particles that are just buzzing around with the fluid. No mass, no inertia. Just think of them essentially as fluid molecules. Inertial particles. These are particles with a diameter and density. They have a non-zero Stokes number. They can settle as work, but they're not interacting. They don't collide with each other. So they do enact a force in the fluid, but they don't necessarily collide one with another. There's no pairwise potential applied to that type of modeling paradigm. Third, DEM. DEM has density and diameter. In addition to that, they have pairwise particle collisions. So beyond the inertial, they also see each other. They bounce off each other, as it were. They can stack. They can form a mound, as it were. We'll speak that later on. And last, I'll talk about this idea about resolved versus unresolved. And that's the question about how fine the grid is with a spectral resolution. Let's get to applications and we'll kind of cascade through the talk. Okay, let's talk about these types of particles. So in this simulation, I have all three types. Let me illustrate just kind of conceptually what's going on. I have 1 million DEM particles I'll be adding, 1 million inertial particles, and 1 million massless tracers. And I'll play this here a couple of times, show what's going on. The DEM and the inertial, at early times, they show very similar results. They're both falling due to gravity, right? Because they have mass, because they have a density, and the density exceeds that of the fluid. And they fall in a very similar way, which makes sense because they have the same physical properties. The DEM are, of course, touching each other, but at that particular injection region there, those collisions don't mean anything. The tracer particles, conversely, the tracer particles in blue, they just kind of hang out. They're just colored molecules. They don't fall. They don't move until the fluid comes and sweeps them away. So as these guys go through space and time, blue has to wait to be swept up by the fluid, as it's discharged by the impeller. Green and red, inertial and DEM, they can fall. They have non-zero Stokes numbers. Importantly, red can mound. You see that down there? Red can form a mound at the bottom because, quite frankly, it has particle interactions. The blue massless tracers just homogenize throughout. They get dispersed. There's no reason for them not to. The red, due to their inertial, form a mound down there. The green is well settled. We'll take a more close look at those momentarily. But these are kind of the key differences here. Massless tracers, no mass, no diameter, no density, Stokes number of 0. They can't grow or shrink. They don't interact, but they're very useful for predicting things like a dispersion, mixing, resonance time distribution, etc. Inertial particles have a mass, shape, and density. They evolve according to Newton's second law, in accordance with local fluid forces, as it were, and whatever physical properties they have. They can dissolve, shrink, grow, react, because they have stuff. They have inertia, a mass, which leads to inertia, as it were. And lastly, the DEM particles, all the benefits of inertia with the ability to collide, as it were. So they will bounce off and form a mound. Should I go down to illustrate this point here? Here we've got a mound of red particles at the bottom that are forming like a snowdrift, as it were, because quite frankly, this impeller doesn't have enough gas to get those things at the bottom of the tank. Our NJS, our impeller speed is not at NJS. We're not getting all those particles at the bottom of the tank, which means they're just settling there, forming a mound, as it were. But blue, which has no mass, they get dispersed, of course. And the dispersion time, lo and behold, is correlated with system blend time. We'll speak to that later. Okay, the second key point here, resolved versus unresolved. Unresolved particles are those that are small compared to the Taylor scale, typically characterized via a grid size, as it were. Resolved particles are large compared to the grid. Some key differences. When you're doing an unresolved simulation, you need to apply some sort of drag model, some sort of lift model if you wanted. You need to say how the fluid is acting at that particle using some sort of what I'll call a subgrid model, because you're not explicitly tracking at this resolution how the eddy is shedding from behind this particle, because our fluid domain is discretized to at a level much greater than that of the particle. So we need to instead say, okay, particle, this is what drag force you will see as a function of your velocity and diameter, and maybe the fluid viscosity. Or particle, this is the lift force you will see as a function of your kinematic properties. Resolved particles are different. Resolved particles are assumed to be large compared to the grid. So we're not saying, oh, well, you must have some applied drag model, as it were. The drag comes automatically out of Navier-Stokes. So again, we're solving for the flow around the resolved particle with a high resolution that eliminates the need for us to apply a semi-empirical relationship instead of just let Navier-Stokes figure it out for us. Unresolved particles are cheap, as it were. As we let these guys buzz through space and time, it's easy for us to model hundreds of millions of unresolved particles, especially using GPU native algorithms. Why? Because sorting is so easy. It's very easy for us to sort particles into an appropriate bin when we have a Cartesian Cartesian mesh, which is a hallmark of these LBM-based approaches on GPU. And so these unresolved particles, again, they're assumed to be small compared to the grid. We need to apply some sort of semi-empirical drag in the models or whatnot, but they scale phenomenally well. Resolved particles, you need to have a lot of resolution to model flow around them as well. You already have this kind of repeating loop here. We don't need to specify anything about drag or lift test where that comes out automatically out of the tumbling of the particle and its interaction with the fluid. But we're limited to scale. Realistically, folks, it's hard to get more than 1,000 resolved particles just due to memory constraints. I'll speak to this point at the end of the presentation, but you need like 50 or 100 lattice points around the diameter or radius of that sphere to appropriately describe flow. So if you've got, a 20 by 20 by 20 vessel of these things, that's going to give you 1,000 by 1,000 by 1,000 grid points. You can exhaust your memory pretty quick. So it's not to say there's a physical limitation, but practically speaking, you're going to have a hard time modeling more than a few thousand resolved particles explicitly, just because the fact that it's resolved requires high resolution, which is going to stress the memory requirements of your GPU. But again, particles can be any shape. It's general. It's awesome. We love it, but it comes with a cost. But these are kind of the two differences between unresolved versus resolved, as well as the different degrees of Stokes numbers for inertial tracer. Yeah. So let's talk about kind of applications here, and I'll jump to some hands-on demos as well. Let's talk about these massless tracers. I'll show them just kind of on their own. So again, these guys have no mass, no diameter, no density. And this simulation here, I just fed in a million massless tracers over a 20-second feeding interval. As I mentioned, the Stokes number is 0. They disperse, right? They're essentially just colored molecules, as it were. They don't grow, they don't react, there's no particle interactions, but they're very useful for characterizing how well fluid disperses throughout a system, or how well particles, I should say, disperse throughout a system, as it were. They're very useful for predicting things like dispersion, as I mentioned. For example, we know from kinetic theory that a well-dispersed set of particles should have a mean separation distance, a mean nearest neighbor distance that's related to the volume of the system and the number of particles. And if you squint, you can see, oh, well, that's nothing more than the volume of a sphere, right? Divided, that's the volume here, 4 thirds pi a cubed. Then you have a volume that's just divided by that. That's just an average volume available to particle. That's not an earth-shattering map, but nonetheless, it exists. Like there is this Wigner-Seitz radius that allows us to characterize, on average, what the mean nearest neighbor distance should be. Well, in the code, we can just calculate what the actual mean nearest neighbor separation distance is and see in time how it converges that value. And the time it takes to converge is a very good metric of how long it takes for these solid particles, or these tracers, I can say, to disperse throughout the system. And that's characterized by the blend time. So at very early times, the particles have a very small nearest neighbor separation distance on average. Small compared to what well dispersed distances should be, because they're all bunched up. But as time goes on and they're dispersed, they spread out across the vessel and they snap back towards expectations from first principles. So expectations of a chalkboard in terms of what the mean nearest neighbor distance should be across the Apollo ensemble. So realistically, this is kind of one application of tracers. You can predict dispersion, as it were, for, say, very small particles, how long it takes to disperse and where those particles are going. We can also be a bit more sophisticated here and predict the distribution of nearest neighbors. Now, this is a bit more nuanced, but it's actually incredibly insightful. So statisticians, beyond just telling us what the mean nearest neighbor distance should be, they can also tell us what the distribution of neighbors should be. Said again, some particles may at some point be closer to their neighbors than others. And one particle may be far away from its nearest neighbor. Yes, the mean is well defined based on the total volume and number of particles, but the distribution is not singular, as it were. And so smart statisticians have derived equations that allow us to predict the distribution of nearest neighbors as a function of the Weger-Seitz radius and the number of particles. That we have not developed this from first principles on our own accord. It exists in statistics textbooks. But at the end of the day, here again, we can watch the system's nearest neighbor distribution function evolve towards predictions from first principles systems. Then again, here's our Weger-Seitz. Again, there's our kind of our mean nearest neighbor distribution function. Here's our most probable, as it were, and that's the actual distribution. And at early times, when particles are all bunched up, that both the mean, the most probable, and the shape of the distribution is more like a delta function than this more Gaussian shaped thing that we realized when it's well dispersed. As we move through time, this distribution snaps towards expectations from the systems. And so again, beyond just looking at some sort of aggregate system level value, we can see not only the distribution and how the system is evolving towards that distribution. I'll show that in action. Like here is the dispersion system, and here's the time evolution of the expected PDF and the realized PDF. Remember, for the first 20 seconds, we're adding particles. So the expected keeps adjusting once we add more and more particles. And eventually, once the addition stops, that distribution is fixed in space, and the realized distribution converges towards it. I should have played this at the end, but you'll get the point. Here we're marching through time. We're still adding particles, adding particles, adding particles for the first 20 seconds. Eventually, we stop adding those particles, and the particles then just homogenize across the reservoir. So there we stop. There we stop. So the same logic applies here. At early, I'm adding more particles, adding more particles, adding more particles, and then eventually I stop adding particles, and the system can then evolve towards expectations from first principle systems. And so there's really tracers, although simple, are really compelling in terms of understanding how things are distributed across space and time, how things are dispersed, how long it takes for things to disperse, and how well that dispersion agrees with expectations from a random assembly of particles, which is kind of cool because not all particles have the same nearest neighbor separation distance. Be able to kind of recover expectations of first principles. Pretty cool. Pretty cool. Okay. Tracers are also phenomenally useful for predicting things like residence time distributions. Again, we just have colored molecules. Here's an example of a scaled down wastewater treatment facility. And I'll show a picture of this momentarily. We have two impellers here, inlets on this side, outlets over here. And we had a measured RTD shown in blue, and then just a comparison to theory for 2 tanks in series. You might be saying to yourself, well, that's 1 tank. Why are there 2 tanks in series shown in red? Well, the impellers were counterflow. They're spinning in opposite directions, which by design introduces 2 mixing regions. And the point of this is to show, look, with 1 tank and 2 impellers spin in 2 different directions, we can recover an RTD that mimics that of a 2 tank in series system using 1 tank. And it's a well-known engineering practice. But at the end of the day, this is the system at hand. Here's kind of a more schematic description. We have fluid flow coming in, 2 opposite spinning impellers, outlet flow here. And again, this is the measured RT that compares reasonably well to the 2 tank system. It's not ideal, of course. There's a minimum time of flight, as it were. But this is what was measured. So we can use tracers to simulate this. And yes, we could also use a scalar field, but tracer particles are phenomenally useful because they have no numerical diffusion. Then again, when I pulse these tracers in, and here they just came in, they're evolving explicitly according to the instantaneous fluid velocity. So look at the fluid velocity, multiplied by time step, updates. There's no diffusive component, okay? And sometimes diffusion is good, but in a lot of industrial processes, when you're doing CFD on them, diffusion is a problem. Numerical diffusion is a problem. Because numerical diffusion is typically orders of magnitude greater than physical diffusion. So particles are cool because they have no numerical diffusion, I should say. So here we go, watch these particles go. And you can see again, they're kind of evolving in accordance to what we'd expect. We're getting 1 mixing zone here, another mixing zone here. A couple of these particles are going to buzz on out and reach the exit, as it were. I'll continue this on. But again, by tracking how long each particle exists inside the vessel, and by tracking what its age was when it exited, we can run this thing for 4,000. We can run these simulations for hours of physical time on GPUs, of course. This didn't take more than, I think it was maybe a day of runtime, if that, to run maybe an hour and a half of processing time. They're starting to exit. I can record their exit ages, as it were, and I can recover something like this. And it's pretty cool. So the green is the predicted RTD. that's predicted by looking at the exit age distribution of the tracers that left the system. Pretty lit. You know, we get the minimum time of flight pretty close, which is neat. We get the mean and most probable pretty right. I should have added more particles. I only added like 20,000. I should have added 200,000. So I was really getting skinny on statistics as they got to low values because I was using discrete tracers. I should have put more in there so I could have run longer. But foundationally, the shape of the profile, the agreement with theory, the minimum time of flight, as it were, that snaps into place. And that's a really cool application of massless tracers. RTD, dispersion, they have utility. They're small but mighty. They can do reactions. They're not going to bump into each other. They're not going to settle, as it were. But for RTD, dispersion, etc., very useful, very cheap, very illuminated, as it were, for illustrating how fluids move through the vessel. Let's talk about these inertial particles. As I mentioned, these guys have mass. They're not colliding with each other, but they do have density, they have a diameter, they have a non-zero Stokes number. And what I mean by that is they can detach from the fluid streamline. When I say it has a non-zero Stokes number, it means that the particle can detach from the fluid streamline. Tracers can't. They're just following the fluid streamline. These two. Now, but they have no collisions. And so what happens is for these guys, look, like, yes, as I mentioned earlier, the impeller speed is insufficient to get these particles on the bottom of the tank. And I have a million of these guys as well, just as I have the DEM. Look at that. They just form like this infinite skin. They're just stacked on top of each other, right? Kind of wrong. Like, what I'm trying to say here is, like, you know, that wouldn't be what happened, because in reality, a particle with a given diameter and a given mass and a given stiffness, which a material will have, they're going to collide and mound, as it were. Inertial particles can't see that. That doesn't mean they're not phenomenally useful. It just means they're not useful when you have extensive settling or you have a very high number density or solids volume fraction. I'll speak to that momentarily. But again, you can see we're getting physics that the tracers don't give us. We're getting detached from the streamlines. We're getting settling. We're getting inertial, as it were. So there are physics here, but it is missing some things. And those missing physics must be noted. The missing collisions lead to kind of particles stacking on top of each other, as it were, which wouldn't be physical, but we can tolerate that if our number density is sufficiently low. So these are exactly what we did for the bubbles, if you remember the last seminar. Whenever we do bubbles, as it were, and here's a secret, if I peel back the veil behind M star, okay, get ready for this. Bubbles and solid particles, they're the same thing. Just don't tell anybody. It's like trade secret, okay? Newton's law, second law, works for both bubbles and particles. Just keep it on the DL. It's just been you and me and everyone on YouTube that watches the DL. But it's the same physics, as it were. It's just different density. But when I was doing this last time, these bubbles, as it were, these were inertial particles, as it were. They collided and underwent coalescence and breakup events, as it were. But foundation, it was the same physics. It was the same kind of looking at some sort of Newton's second law, prescribing some drag model, as it were, and watching these particles evolve through space and time. So it's the same physics that I've seen in the past 2 seminars. This time the particles just have a higher density than the surrounding fluid. But importantly, these are great for kind of low density solid systems where collisions may be infrequent, particularly for low density dissolution processes and suspension. So for example, NJF, so maybe dissolution, as it were. So here we're trying to get these particles on the bottom of the tank, and we have a very low solids fraction, as it were. They're great for this type of application, where I'm looking at how different impeller speeds might inform the settling characteristics of these particles. And here I can see at 50 RPM for this PBT, like I'm getting particles stuck at the bottom of the tank. Like no matter which way you cut it, the number density, the residence time being greater than 1 second or whatnot, I can see that this impeller speed is not sufficient. That is, the momentum of the fluid is not sufficient to suspend these particles. Tracer particles wouldn't give this to you. You need inertia to be able to capture that effective settling on the trajectory of the particle. At 120, I'm doing better. In fact, I could squint and I could be more rigorous here, and I will momentarily, but I convinced myself that those guys are suspended. They're not spending more than a second at the bottom of the tank. The number of particles at the bottom of the tank is not changing with further increase process of work. So inertial are useful. Yeah, they don't hit each other, but in a low density system, in a low solid fraction system, they're still very useful, and they're far cheaper than trying to look at DEM particles. I'll speak to momentarily. Not that DEM is super expensive, but they're cheaper. We don't look at for pairwise interactions. So we can use this to do stuff. Like we can predict as a function of impeller speed how many particles we have on the bottom of the vessel and say, aha, as we get above, say, 100 RPM, the number of particles stops changing. At lower RPMs, we have more particles because they're settling. At higher RPMs, physics stop changing. We can do this with different impeller types. An A510 is a counterfoil. The A200 being a PBT. And so we can look at these guys here and say, okay, well, you know what, these different impeller speeds eventually get speed independent characteristics. And importantly, we can change this to compare this to measured data. And when you go in the lab and measure the NJS, the impeller speed required to get all the particles on the bottom of the tank, it agrees quite well with the speed that we were predicting from the simulation of inertial particles as being the speed at which physics stop changing. So again, these inertial particles are very useful, particularly in systems where gravity matters, particularly in systems where buoyancy matters, and particularly in systems where the particle to solids fraction might be low, as it were. So don't discount the fact they don't collide with each other. In fact, they're kind of a sweet spot in many simulations where particle collisions don't matter. And in fact, this NG has been very well validated. I don't know if Chattercon's on the call today, but she did a great work on this a couple of years ago, where she systematically looked at different impeller types, clearances, etc. Was able to show that with this one simple modeling framework, these little rinky-dink inertial particles, they can capture a very broad spectrum of suspension characteristics, as it were, without having to do a lot of lift. So again, inertial particles are almost free within the context of simulation. Yeah, you get about 10 million of them, you'll sort of feel it, but you can do tens of millions of inertial particles and not even notice it in the context of your simulation. Okay, inertial particles are also very useful for things like dissolution. And I shout out to Sartorius, who's working with us, who we're working with on this. Again, because inertial particles have mass, they can participate in reactions. They can dissolve, as it were. And if your loading fraction isn't particularly high, and in most dissolution systems, you don't want to form a clump, like you're feeding this stuff in at a rate that prevents clumping, inertial particles are a good choice, as it were, because your solids loading fraction by design isn't going to be super high. And so the additional cost associated with DEM might not be worth it. It's worth looking at just simple dissolution process for batch preparation. So in this thing here, they got some special impeller, which actually behaves very well in terms of producing radial flow along the bottom of the vessel to kind of keep these particles off the bottom and suspended. And they have kind of different addition times here of the salt, as it were, and the measured conductivity. They have a conductivity probe in there, and they're measuring how that conductivity probe evolves in space and time. Evolves in time to recover some total mixing time, become steady as a function of these different kind of injections. These injections, admittedly, from the application are kind of cartoony. That's when they started the injection. It might have taken them 10 seconds to add all the crystals, beginning at 2 minutes, 3 minutes. It wasn't just like, boom, they just dump them in at 2 minutes, as it were. There was some ramp up time, but at the end of the day, it does give you an idea of this kind of periodic pulsing and how it informs the evolution of the conductivity. Dead particles, they dissolve. Okay, let's look at just the fluid flow first and look at how this impeller behaves. And it's actually a pretty well-designed system. It gets a lot of radial flow and does a great job of discharging those particles out, and it's going to get them suspended as well. So look at just the Y velocity here. Lots of Y velocity on the wall. Now, up positive Y velocity, whereas it discharges the fluid up and then recirculates it down in the center region here. Again, this is an impeller fit to purpose. It's designed to do bottom clearing suspension to avoid mounding, avoid settling where possible. All these are kind of dog whistles or keywords for I bet inertial's okay. We were able to get some estimates on the particle size distribution, as it were, and what shapes these particles were. There are all sorts of different species going in this part of this problem prep: salt, base, HCl, etc. All sorts of crystals are going in an attempt to kind of create this ideal buffer solution within their characteristic, within their physical system. Now, again, within the model, when we're using inertial particles that are unresolved, which is the case here, we do need to specify some sort of transport relationship. Like just as I said, when we need unresolved particles, we got to describe what the direct relationship is. We're not modeling the flow eddies around the particle explicitly because they're very small compared to the fluid element size. Like that, also by induction, we also have to specify something about the convective mass transfer relationship. If we had incredibly high resolution and could do resolved particles, we wouldn't need to do this. We could use the first principles film theory to predict mass transfer. But since we don't have that level of modeling fidelity, we have to resolve these unresolved particles. We do have to appeal to some sort of semi-empirical mass transfer relationship. Here's a common one off the shelf, as it were, is we're going to model the dissolution rate, the KL, as it were, of each individual particle as it buzzes around this tank as a function of the local particle Reynolds number and Schmidt number, as it were. So we're going to, again, because we're unresolved, we have to appeal to some sort of correlation here. And we might argue about the function of this correlation. We want to find one that's general, to be sure. But foundationally, recognize this paradigm exists. For unresolved, we have to add in the missing physics. In this case, the missing physics is the boundary layer. And in this case, we need to resolve what's going on inside the boundary layer using some correlations. So this isn't a bad one. It's a great correlation, but recognize we do have to appeal to something. So what does this look like? So I'll play this a couple of times. So here I have particles coming in. I'll add them after the fluid gets agitated a bit. The impeller is in fact spinning. It's just the frame rate of my movie makes it look like the impeller is static. In reality, it's buzzing around. That's where you get the vortex up there. Here come the particles. I'll have them dump in here. Okay. So here are the particles that are settling because they're inertial particles. They have gravity. And this colored continuous phase, that's the salt concentration. That is the salt that's being transferred to the aqueous phase due to this KL. And this KL is occurring on a particle by particle basis. So for every single particle that comes into the system, we are looking at its individual particle Reynolds number. We're looking at its individual concentration in each of these species. We're looking at the concentration in the dissolved phase immediately surrounding each particle. And on a particle by particle basis, tracking and calculating the individual mass flux from each individual particle. That then gets aggregated across the entire particle set to produce this spatially varied accumulation dissolved species. On a particle by particle basis, we are having that mass transfer inform the size of the particles. So as these particles dissolve, they shrink. And all these physics are coupled. I'll say the daisy chain again. Particle falls in, particle realizes on a particle by particle basis, convective mass transfer with the surrounding fluid as a function of the fluid properties and the concentration, as it were. That mass transfer increases the concentration of salt in the aqueous phase and decreases the diameter of the particle for the density, as it were, for the particle density, or the molar density. So here, as we watch this guys go, I'll stop this one more time. We have this cloud of salt throughout the system that has been deposited into the vessel, into the fluid, via convection, mass convection from each particle. Some of the particles made it to the bottom without fully dissolving. That's fine. That's fine. Some of them are going to splat. Some of the larger ones are going to hit the bottom, and they're being pushed radially. And as time goes on, we're whisking all of the mass away from each of those particles, and the system fully dissolves. I'll play that in a few times. And also we have this mixing process throughout the thing as well. These corners are the last to blend. The particles hang out there the longest, as it were. Eventually they'll disappear. But you get that little mound there. There's only so much that impeller can do in pushing out the corners. They're almost all gone. As expected from the experiment, it takes a few minutes for every last particle in the corners to hopefully homogenize. But we're there now. I'll play that again because there's a lot of physics. Again, particles come in. They are immediately start dissolving, leading to, again, this cloud here is the electrolyte concentration, is the salt concentration, is the concentration of the dissolved stuff, as it were. You can't really see it until you get to the end of the simulation, but the particles are getting smaller as they give up their material, as they should, because mass is conserved. And that mass they're giving up, the species are giving up as it goes in the aqueous phase, comes the cost of their diameter, as it were. And so the reason these particles disappear is not because like some optical illusion. They're disappearing because they're giving up all of their mass. All of their mass is becoming this dissolved concentration throughout the system, as it were. So you see this ongoing competition between mixing, dissolution, particle shrinkage, etc., and particle dispersion. And again, I will say the injection was kind of cartoony, and it's not a slight against technical document. It's just acknowledging that we don't know exactly whether this pulsation occurred over 30 seconds or 1 minute or 10 seconds, as it were. We know that's when they start the pulse. And to be sure, kind of the highlights are here, though. the highlights, the fact that once we induce a pulse, that it takes a minute or so for that pulse to completely dissolve. The fact that it can, after its last pulse, within a couple minutes, be fully converged, as it were. Those broader strokes, we're getting right, as it were. And importantly, we're getting it right using semi-empirical theory and doing this on a particle-by-particle basis, okay? Which is kind of cool. And what's neat about this, guys, is that all of these models, they're not tailored to this vessel or this particular injection profile or this square tank or this level. This semi-empirical theory is general, which means that if I change the tank, change the impeller, change the fill rate, change the fluid height, change the oxygen ratio, I don't change my theory at all. I have one theory to rule them all, and that's when a model is good. And that's the point, as I said on the second slide, of going down to transport models at the level of the individual carriers, in this case, the particles and the eddies. Let's talk about DEM particles again. DEM particles are awesome. They have mass. They have diameter. They can dissolve. They can react. They can grow. They can also mound. So here we have, this is about 1 million DE. I added, and I'll show you the model momentarily here. I added 50,000 per second, 1 millimeter diameter particles for 20 seconds. Here I can see that just kind of that flowing snow, as it were. These are hot, right? Not hot like temperature, these are like lit, you know, in the parlance of teenagers. I have a 13-year-old son, so lit, that's my parlance. It's but at the end of the day, it's like there's a lot of physics there. They're more expensive than inertial particles, but not that bad. They're not killing us. And again, this is where the idea of resolved versus unresolved really comes into play, okay? This is unresolved particles, as it were. So here we're watching these DEM particles plow. We're watching them dissolve in this case, and the particles will get smaller, as it were. But in all cases, the particles here were small compared to the grid spacing. So let this guy cook a bit and let him go. And you can see the particles are dissolving. They're getting smaller. This is everything. Multi-phase, dissolution, changing diameter, CFD DEM. This is everything, as well. It's kind of cool to see all those physics going on in tandem. You can see they're getting smaller. They're shrinking. They're losing diameter. This is CFD DEM with coupled chemical reactions. And I'll kind of, you got the image. They're dissolving. They're going away. Here is another example of unresolved CFD. So here I have just particles kind of coming in this baffled pipe, as it were, and we're watching them mound. Like the fact that they're mounding right here, like that is a bell ringer for DEM. Like inertial particles wouldn't do it. Inertial particles would form like this infinitely thin layer here of all the particles just stacking on top of each other. But when you have DEM, you can start to appreciate how these different mounds and pockets form. I'll play that again here. So watching some of the smaller particles have no problem sailing through. The smaller particle, I had a range of diameters here in terms of my DEM particles, one from 1 to 2 millimeters. Tiny guys make it on through. Heavy guys have a way of getting stuck. Lo and behold. Here's the top view, kind of watch that guy plow, as it were. But again, these are not expensive simulations. You know, this is maybe like 10 hours to model 30 seconds. I think it ended up with maybe a couple million DEM particles when all said and done and settled in this case. But this was not a particular 3D simulation. But importantly, these are all unresolved DEM particles. We're assuming that they're small compared to the grid spacing. This is resolved DEM. This is where the particle is large compared to the grid spacing, and we are tracking how those individual particles are informing fluid flow and how the fluid flow is informing particle trajectory. We don't give these guys a drag model, as it were. The drag naturally comes out in outer Stokes, okay? We don't give these guys oftentimes some sort of generalized KL expression. We'll use two-film theory, as it were. And so foundationally, it's a much more taxing simulation, but it may be necessary when you have like a capsule dissolving or some sort of larger platelet or some sort of larger object that's tumbling through the fluid. And again, harken back to what I showed earlier. The unresolved particles were tiny compared to the grid. The resolved particles are large compared to the grid, and they got to be very large compared to the grid, like 50 points. The diameter of the particles got to be like 50 points bigger than the grid to accurately resolve the flow field around it, and so on. For tiny particles, one thing just to be smaller than the grid. So again, we do have coupling here because these are CFD DEM simulations. So we do have, of course, particle-particle forces. So each particle has a host of properties. It has, you know, a modulus, a Poisson's ratio, a diameter, a velocity, a position, etc. And we can describe through arbitrary contact mechanics what these contact forces will look like. 99% of the time, people use a Hertz contact model because it's simple. But at the end of the day, it can be arbitrary. I just use Hertz in the sky with some given modulus, Poisson's ratio for each particle. But you can do whatever you want to do. But at the end of the day, there's some contact mechanic. You also have fluid particle forces. That is, there is drag force, for example, on this particle, and so forth. And there's going to be a reaction force on the fluid, right? We have these fluid particle couplings, of course. Likewise, in many instances, we have a particle viscosity element. So again, the viscosity of the fluid may be a function of the solid's concentration, okay? And this is not uncommon, as it were. But again, these are all the ways in which this particular model, the particles and fluids are coupled, as it were. We have reactive forces, we have viscosity inferences, we have particle interactions, of course. And the beauty is this, is because we're doing all these particle mechanics in tandem with the CFD, these couplings are simple, right? It's easy for us to describe how the viscosity is changing in time if we know how the particle concentration is changing in time, and use that changing viscosity when we're solving Navier-Stokes over time, right? Because all these physics are coupled, this idea of a spatiotemporal viscosity due to changes in the spatiotemporal solid distribution, sure, that's not a problem. We're doing that now when we're solving all these physics in tandem and in real time together. And again, this is particularly useful for things like fluidization, packed beds, and so forth. Again, kind of looking at how, as a function of gas flow rate, I'm trying to move your bit more quickly, how we suspend a fluidized bed. Again, if we're kind of stepping through various inlet velocities here, kind of watching how this bed height changes as a function of increased velocities. This is all unresolved DEM. Those particles are small compared to the system domain, as it were. But foundationally, these types of models are very useful for predicting things like fluidization and whatnot, where if the bed's not fluidized, it becomes packed. For antennas of DEM, we need collisions, as it were. These are very useful for things like blending as well. Here's this is the courtesy of Corteva. We presented this last fall, looking at things like, how these screw dryer systems blend, as it were, kind of coloring these guys by two different colors and watch the entropy of mixing evolving over space and time. This is a great application of DEM, looking at, again, how these beds mix. We can look at, drying as well. Here are particles, they can, again, because they can participate in transport physics, we can actually watch these guys warm up as we put hot gas into this vessel. So again, we can model convection from the wall using semi-empirical theory. We can model advection diffusion of thermal energy inside the bed. We can model convection heat transfer from each particle, as it were. Using, again, because unresolved, we need a semi-empirical theory. We can pull that off the shelf. We can model heat vaporization as it loses moisture, as well as particle conduction. Like all these physics, all these particle to liquid transport physics, those are in play and easy to solve, as it were. Likewise, mass transfer. Here we can watch how dry nitrogen moving through this system ultimately reduces the moisture content of the particles below. I don't have this one going for very long, but if you squint, you can see the particles near the bottom of that vessel, those closest to the inlet where the hot nitrogen is coming in. They're dry, their water content is going down. Again, we can track, using these TM particles, how these individual physics, as it were, and how these coupled transport relationships are evolving in space and time. And again, importantly, we wouldn't be changing this. Like if we used a different screwdriver, or maybe we're shaking instead of just stirring, as it were. These semi-empirical theories, they wouldn't change, as it were. They wouldn't change at all. Okay, let's go ahead here and continue on. Oh, and there's actually the water concentration in the aqueous phase. And again, as I said before, as the particles are giving up moisture, that moisture is going somewhere. It's going into the gas phase here. It's being swept out of the system. So that's the actual moisture composition of the air that's going into the air as the particles dry. So all these physics are really nicely coupled, as it were, when you're solving them all in real time and in tandem. And resolved DEM, this is kind of the holy grail here. These are the most expensive simulations, because not only are you looking at particle-particle collisions, but you need to be able to see flow around and through this packed bed. So these are really cool when you're doing like a packing simulation and then modeling flow through it. That one's kind of turkey on the machine. But when we're packing a bed and looking at flow through it, that's where these things really shine. Very useful for looking at things like flow through packed beds. Very useful looking at things like a fluidization of a vessel with particles that are large, as it were. And we can do some neat things. We can look at, say, the pressure drop as a function of resolution and say, aha, here's where that rule of thumb, 40, 50 points across the particle diameter comes from. Because if we don't have that resolution, we can't get a converged, say, pressure drop. Look at a flow through packed bed. And this pressure drop is in good agreement with ergon relationships, et cetera, for similarly packed beds. But this is where resolved DEM really comes into play. Again, you can do packing with it, which is great. These are the most expensive simulations, but their fidelity is phenomenal in terms of watching flow, multi-phase flow go through this packed bed, as it were. Watching how that packed bed might jiggle around, should it be agitated, as it were. These are the most expensive simulations. We've gone from massless tracers to fully resolved DEM, but foundationally, between that spectrum, you can do a lot of physics. Okay, let's kind of give a roadmap here about what we've done and kind of where you want to use each. Tracer particles, awesome, cheap, great for visualizing flow, no numerical diffusion, useful for predicting dispersion, useful for predicting RTD. You don't get settling, you don't get you will not get reactions, as it were, but they have a role. Inertial, unresolved, cheap to run. Resolved get more expensive. They don't have numerical diffusion, and they can be coupled to scalar fields. They can dissolve, they can react, they can grow, they can shrink, as it were, but they don't consider particle-particle collisions. DEM, unresolved, a little expensive. Resolved, very expensive. Right? Like, it's hard for me to do more than 1,000 resolved DEM particles. So that would imply that I have something like 1 billion lattice points. Doable, but big. Okay, doable but big, and limited on scale, as it were. That they model particle interactions, and they can be used for coupled scalar fields and particle settling accumulation. And so, kind of the roadmap here looks like this. This x-axis here is describing the size of the system, the vessel, relative to your particle diameter. T is the vessel diameter, D is the particle diameter. If your vessel diameter and particle diameter are similar, that implies like a scale of 1 to 10, like your vessel isn't much bigger than your particles, as it were, you're down here. If your vessel is huge, if your vessel is like 10 meters in diameter, and your particle is 1 meter in diameter, 1 millimeter in diameter, you're over here. Okay, you're over here. This describes the volume fraction of the solids. If you have a solids fraction that's like 64%, or like 50%, or 20%, like that's a lot of solids. Okay. If you've got a very low solids fraction, like less than 1%, or just a fraction of a percent, that's down here. High solids fractions, low solids fractions. Big particles relative to the system size, tiny particles relative to the system size. These boxes describe where you use what and when. The left-hand side is limited by physics. The right-hand side is limited by memory. Ideally, if we had unlimited computer resources, we would do everything as resolved DEM, all the way up to huge systems with tons of particles. That would require inordinate resolutions. It's not practical, but in principle, we'd love to do that. We'd never make any assumptions, as it were. But for all practical purposes, you're not going to be able to run a resolved DEM simulation where the packing fraction is like 50%, and you got a vessel size that's like more than like 10 or 20 times bigger than the particles. Like, as you get above that, like this represents like 1,000 particles. It's just where we're at now with modern computer resources. If you've got fewer particles, God bless you, go for it. It doesn't hurt you to have fewer collisions, as it were, and few DEM particles down here, as it were. You can do a resolve should those particles be large compared to vessel size. So if you have vessels that are large compared to particle size, resolved DEM is great. We'd like to do resolved DEM for everything, but again, memory requirements limit us to maybe like 20 or 30, I'd say, particles across the diameter, as it were, which gives us this like 1,000 particles across it. If you get bigger, if you get a bigger system, as it were, and have a high concentration of particles, you're going to want to jump to an unresolved DEM. That same idea here, where we have particles that are small compared to the grid and or integral scale. These are cheaper, as it were. We can typically do this up to maybe systems that are like 100 to 1,000 times bigger than the diameter. But here again, we got memory problems. Like, just as we can't do more than like 1,000 resolved particles to the grid spacing, it's hard to do more than like billion DEM particles. You can do it, but as you get to like to the right of this line here, implying that like your particles are like 1/1000th your tank diameter, and maybe you've got a packing fraction at 50%, that's like a billion particles. That's getting harder, okay, to do memory. Like we'd love to use unresolved for everything, but again, it gets harder from a memory standpoint. So the real sweet spot here is if you got more than 1%, and your particles are between maybe like, 50 times smaller than your vessel up to maybe like 1,000 times smaller, unresolved DEM is good. You've got fewer than that, and the particles never seen each other, if they're never even bouncing off each other, then just go to inertial. Like if you've only got 0.1% solids, don't waste your time with DEM. There's no point to it, right? Like they're never going to see each other. Just use unresolved inertia. If you have a huge vessel compared to your particle size, well, eventually, guys, you're approaching like molecules, okay? And it makes more sense to use that as like a scalar field representation, where rather than modeling every individual particle, you're just treating it as some sort of like effective concentration, which is moving via advection diffusion throughout the vessel. And so foundationally, very, very, very small particles relative to the tank size. And if the concentrations are low, just use a continuous scalar field, as it were. In the opposite corner, this is where correlations still operate, guys. This is too hard to simulate at this time. Huge vessels with huge solids fractions, like you can't model them all. You got to use like an ergon model. You got to use something else, as it were. So this is kind of, I hope my grandchildren's grandchildren will be able to use simulation to access this, but put it on my tombstone. I don't think we'll be doing simulations out here anytime soon. That's not morbid, but hopefully I'm proving wrong. Hopefully I'm proving wrong. But at the end of the day, those are very expensive calculations. So most this is kind of your B dragons, use the scalar field. These are kind of the sweet spot, these types of ideologies. Guys, we covered a lot. I wanted to jump through the model and show this in action. I don't think I'm going to have the time to do it. But if anybody wants any of these models in MSTAR, and I can send them out immediately. There's no problem at all. Everything I've got here, I can share most of them, except the models that were done with collaborators. But all these things here, you can have them. You can see how I built them, see how I added them, see how I analyzed them, etc. All these things are available for you. There was the results here. I wanted to show some of this, but I had too much crammed in to this exciting hour. Okay, I'll leave it at that. We've got a few minutes for questions. Thank you for populating them. And Amber, thanks for giving me the floor. I'm happy to speak any questions folks have.
Okay, first question related to the resolved particles. Is a suggestion of the minimum amount of these lattice sites related to the entire circumference of the sphere or the radius of the respective sphere?
Well, I mean, choose a factor of 2 pi. I mean, at the end of the day, I've been using diameter. And what's motivating this is kind of like my work like this. I didn't mean to be cheeky with that choose factor of 2 pi, but it's like, at the end of the day, I could convert this into number of cells per sphere circumference, but this is with respect to diameter. And so why do I keep saying 40 to 15? I usually see when I look at flow through packed beds and fully resolved DEM particles that things like pressure drop and mean velocities, they stop changing once I get like 40 to 50 points across the diameter. Because what we really got to see there, guys, is the interstitial region, right? And so if I have too coarse of a resolution, I'm not seeing the gaps. I'm not seeing that flow field well enough through the particles. But as I get about 40 or 50, generally speaking, in my cases, my physics become pretty grid independent, which is why I come up with these rules of thumb, 40 to 50 across the diameter, which, sure, let's make it 300 across the circumference, speaking, but that's kind of where I'm coming up with that rule of thumb.
Okay, is it always quote unquote better to use particles to determine blend time compared to a scalar, or due to the numerical diffusion, what are the trade-offs?
Great question. Not always better. And I'll tell you why. There's something to be said for the additional degrees of freedom presented by a scalar field. When you're modeling scalar transport across the fluid domain, the number of sampling bins you have is equal to the number of lattice points. And so realistically, if I have like 10 million grid points, I have 10 million individual bins that have to kind of converge the same value across the scalar field to indicate homogenization. For particles, if I have like 1 million particles, my precision is limited by the number of particles I'm tracking. So if I have 1,000 particles at a blend time, my answer won't be as precise as what I would have gotten by using 10 million individual voxels to characterize how homogenized the system is. And so if you use, let's say, like 10 million particles, in fact, you probably would use like 100 million particles to replicate the granularity of a scalar field. You'd probably recover the same blend time as would be predicted from a scalar field with no numerical diffusion. Yes, you have the advantage of no numerical diffusion particle field, but quite frankly, it gets pretty expensive to match the precision of a scalar field. And so realistically, yeah, you can do blend time with particles. You do eliminate numerical diffusion, but you also limit precision because the degrees of freedom you've been used to characterize the degree of mixing are order of magnitude smaller with particles than they are.
Okay, I'm going to jump ahead. I think we've answered a few of these questions already in your presentation. Can we model reactive precipitation systems or cooling type crystallization and predict particle size distribution?
Okay, so whenever you have like a nucleation or some sort of stochastic event, you can do that in a model, but beware, you've got to put the hand of God in the simulation to determine like what are the conditions that lead, excuse me, towards the spontaneous crystallization or precipitation event. You can do it, but like for any of these kind of chaotic or non-deterministic systems, for example, M-star random numbers are available to you, but you would still need to like determine as a function of the fluid properties, this is the probability that a nucleation will occur, and then maybe sample from a random number to determine whether or not you will nucleate. So you can do it, but if I went online and said, oh, good news, guys, I've got these universal rules for precipitation precipitation, you should leave. But if I come to you and say, guys, you can do it, you can access random numbers in M-star, and you can on the fly change the conditions leading to precipitation and or nucleation by appealing to random numbers, yeah, you can do that. So in play, doable, but you've got to make sure you're thinking about your the random numbers driving precipitation nucleation correctly.
Okay, how many more questions do we take? Or
we got one more minute with respectful time.
Okay.
Fire one more.
Okay, let's see. For unresolved DEM particles, are there particular drag models in use? In particular, I was wondering how to adjust drag and particle-particle friction if my particles are particularly rough or non-spherical.
Yeah, at the end of the day, the playbook available to you are the properties of every particle, including the one with which it's interacting, as well as the fluid properties around that particle. So we have kind of simple, whether it be semi-empirical isolated sphere or packed bed drag models, but really the playbook is open, right? You can write your drag model to be a function of any fluid property or any particle you assign to it. So if you had a model that was surface roughness dependent for describing drag, and you assigned a roughness to each particle, then you could evoke that roughness and write the drag model to account for that physics. So I don't have an example of that now, but the playbook is there. The playbook is there as well.
Okay, well, thank you so much for your presentation today, John, and thanks to all of you in our audience who have taken time out of your day to join us. I just want to remind you that this webinar has been recorded and it will be available to access soon on our website and on our YouTube channel. And please reach out if you have any additional questions or if we didn't get your question answered in today's presentation.
Thanks, guys. Appreciate you.